While Star Trek brought us many technological advances and possibilities for what humanity can be as a civilization, perhaps the most groundbreaking of all was the invention of warp drive, which enabled us to travel to the stars. Even before Star Trek, it appears that defeating the speed of light was a requirement for human space exploration. In this video, we'll take a look at everything you need to know about warp drive. Most of us who are alive today have never known a world without human spaceflight. Yet, before we walked on the moon, built an international space station, and sent spacecraft to all of the planets and even beyond the solar system, there was Star Trek, which installed even bigger dreams in the public imagination. Our ships were propelled by antimatter technology rather than rocket fuel. We arrived at new planets around distant stars rather than the nearest world in our own solar system. Instead of breaking the sound barriers, we traveled light years in a matter of days. Given that the nearest star to our sun, and the next potentially habitable world, is more than 4 light years away, a journey to any other star system would require multiple years back on Earth, even if the ship used special relativity to shorten the journey for the crew. While traveling near the speed of light, Einstein's theory states that distances in your direction of motion appear shorter and the rate at which time passes appears to slow, two of the most counterintuitive but well-studied and confirmed consequences of special relativity. If this was the only way to travel through the universe, only crew members traveling at near light speeds would be young, while years would pass at both the origin and destination star systems. Except for very nearest stars, interstellar travel would be a generational endeavor. However, general relativity provides a possible way out of this constraint: the malleability of space-time itself. We may not be able to travel through space at speeds greater than 299,792,458 meters per second. But if we can reduce the actual distances between the two locations, we may be able to travel there very quickly, not only from the perspective of the crew, but also from the perspective of observers, both at the source and the destination. Warp drive, as proposed 50 years ago, provided a unique realization of such a solution. By distorting space along the direction of motion of a starship, science fiction writers first proposed the distortion of space along the direction of motion of the starship in a hand-waving sort of way in the 1960s, with fictitious mechanisms powering it. Warp drive could arbitrarily shorten a journey across the stars, limited only by how dramatically you could shorten the space in front of you. But would it be physically possible? In 1994, it was demonstrated that a solution within general relativity existed that resulted in this exact space-time behavior. Miguel Alcubierre demonstrated that warp drive was fully consistent with the laws that govern the fabric of space and time itself, by shortening the space in front of you and lengthening the space behind you by an equal and opposite amount, while creating a stable bubble of space inside for your starship to reside in. The physics behind warp speed travel, now known as the Alcubierre drive, went from science fiction to plausible science in one fell swoop 22 years ago. Many practical obstacles must still be overcome before the Alcubierre drive can become a reality. For starters, the most conservative estimates for the energies required to deform any non-empty region of space in this manner equates to at least 20,000 megatons of TNT, or a ton of mass converted into pure energy using Einstein's E=mc² formula. Another requirement of the Alcubierre drive is the creation of a region of space with an energy less than the zero-point energy of space itself, which necessitates the existence of negative mass in some form. While this may appear to be an insurmountable constraint, given that only positive masses and energies are known to exist in this universe, a setup similar to the Casimir effect, in which parallel conducting plates can reduce the effective zero-point energy of the space inside, may provide the necessary energy conditions. We've learned that it might be possible thanks to advances in understanding one of the most fundamental laws of physics: general relativity. Perhaps there are other Star Trek fantasies that will come true someday. And with that being said, it's time to end our video. Subscribe to the channel for more amazing videos like this. We'll see you with another interesting video.